Hey, let's take a look at this section here, section 3.1, graphs of polynomials. So we're en route to talk about polynomial graphs in general, and we're going to draw just beautiful pictures in the next few sections, but we're going to have to, we're going to have a whole bunch of definitions in this section, and hopefully this is stuff we've seen before, but maybe it's not, and that's okay. Because anyway, we've got a bunch of definitions. So as much as we can, we kind of want to tie back into what we've already talked about. So let's kind of do that along the way. All right, so graphs of polynomials. Polynomial functions, we want to define this. Polynomials, we know what polynomials are. These are, we can have an example here. Maybe if I've got, a quadratic function, right? Let's actually have numbers in there. So 3x squared minus 2x plus 1, right? This is a polynomial. We know it's a polynomial because it's just, we're going to take x and we're going to multiply it by itself a certain number of times for each term, and then we're going to multiply each term by a real number. In general, when we write a definition for this, it's going to look kind of goofy. Let me just write it out and we can talk about it just a second. Okay, so it looks kind of goofy, but really we're just looking at something that looks like this, right? All of the A's here are representing real numbers, and the number n is a natural number. So we remember what natural numbers are. These are 1, 2, 3, and so on. Okay, well, I guess we should include 0 here, right? So these would be whole numbers. Down here, we're going to make a statement about what happens when the degree is 0. Or excuse me, when that number is 0. Okay, anyway, so yeah, we've got each of these terms, and then we've got a whole bunch of other ones in here we didn't list. Each one of these terms is just our variable raised to a whole number power, and we're multiplying it by some fixed real number. Okay, so in this case right here, we would say that n would be, the largest of all these powers, so that'd be 2. So great. Let's keep going with this definition here. So the natural number n is called, we're going to call this the degree. So it's the largest of all the powers on the variable. The term is the leading term. So the leading term is the term that has the highest power on it. So this one is the leading term. And if we're looking back to the one we've got up in the corner here, that's the leading term right there. So 3x squared would be the leading term. Okay, the real number that is going with the highest degree term, that's going to be called the leading coefficient. In this case here, we would say that it's 3, right? Up in the corner, we would say that the leading coefficient is 3. The real number, we want the constant term, so that's the one with no variable with it. So in that case, we would have 1 as the constant term. Okay, so as special cases here, if we have a function that maybe is of the form, 2, f of x is 2, we would say that this has degree 0. Now, what we want to think about here is the variable part attached to it. Well, we know that any number to the 0 power, that's always 1 for all real numbers. Right? So anything to the 0 power is always 1. So we can think about there being a variable part here just to the 0 power here. So if the number in front is not 0, we say that the constant function here has degree 0. Now this one, if our function is identically 0, if it's just 0, we say this has no degree. 0 behaves very strangely when we get further and further in our math career. 0 starts acting really weird. But for now, 0 is going to be great. 0 is going to do what we want, right? If I plug 0 in to this function up here in the corner, for example, something convenient happens, right? I put a 0 in there, that just goes away, and it's 1, right? So at this point in our math career, 0 is a very well-behaved object, and we love it. But later on, stuff like this in our definitions kind of gives us fits. So I don't know. For now, yeah, 0 is easy for us to deal with, but we have to say, for the future, uh, we have to say that if it's identically 0, it has no degree. And this might come up later on in your math career, or maybe it won't. But heads up if it does. Okay, so we can identify polynomial functions. Exercises like this, we're just going to have to say that all coefficients are real and all exponents are non-negative integers. Now, as long as we verify those two things, which is essentially what we were saying with all these a's are real and n is a natural number, if these two things are true about our candidate for a polynomial, then we're going to say it is a polynomial function. So maybe a couple examples of maybe what's not a polynomial function, right? If I have maybe something that looks like this, this is not polynomial because of this one, right? That exponent, if we were to write that with exponents, we would have -1, right? So this is not polynomial, right? Because all exponents need to be non-negative integers. Other things we might see, examples of things that are not polynomial, are when maybe a coefficient would be not a real number, like square root of -1, that wouldn't be included. Okay, but really the big thing, what we're looking for is the negative exponents or the fraction exponents, right? If I have square root of x, I can rewrite that with exponents, right? That would be a 1/2, and we would say that this is not polynomial. So yeah, the big things are all the coefficients are real, and the one that's more important for us, I guess, is that all exponents are non-negative integers, so they're whole numbers. Great. Okay, so we've got a application problem, or an application problem, I guess. Okay, so let's take a look. We got a box with no top, made from a piece of cardboard. We're going to cut out congruent squares from each corner and fold the resulting tabs. So let's take a picture, or let's make a picture of what this is going to look like. So we're going to start with a piece of cardboard, and we can draw a picture of our piece of cardboard. Check it out. It's 10 inches by 12 inches. And we're going to cut out congruent squares. So maybe we remember what congruent means. Maybe we don't, look it up if we don't know what it means, right? Congruent. So in this context, it means that they're the same size. So we're going to cut corners out of these, and they're all going to have squares that are the same size. And then we're going to take and we're going to fold along those lines, right? So these parts are going to be gone, and I'm going to fold up those corners, right? Okay, so we've got the first sentence. We drew a picture of it. How beautiful. Let's let x denote the length of the side of the square that's removed from each corner. Okay, that's good. We can add to our picture. We got this distance is x. These are all x's, right? Those are all x's. Okay, write a polynomial function describing the volume of the box as a function of x. Okay, so as far as this general problem solving strategy, we're kind of well on the way of solving this problem. So we read the problem, we understand what it's asking. We want the volume of this box. So we kind of surround ourselves with what we know about volume. We know that volume is length times width times height. And we need to express this in terms of this value x. Well, let's take a look at what the box would look like, because this is our base here, right? So that's our base. Maybe I can draw a nice three-dimensional picture here. Yeah, that's pretty, well, yeah, that's pretty poor. Let me start over. Okay, so we've got our base. We're going to have our height. We connect all these pieces. Great. All right, so we've got such a beautiful looking box right there, right? And we have to say what these dimensions are, right? So this side right here is the same as this side right here. And we want to know what is the length there. Well, we can use what we've already got to do that, right? So we want this length, but if I know the whole thing is 12, right? This whole thing is 12 here. How much did we take off when we cut off those squares? Well, I took out an x here and an x here, right? So wouldn't this be 12 minus 2x? So we can write that, 12 minus 2x. And the same thing's going to happen here with our other dimension. If I want this, well, the whole thing is 10, and just take out those two corners, right? So we would have that this dimension here is 10 minus 2x, okay. And then the height, well, that's what we cut out of the box. Okay, so now we've got it. And it doesn't exactly matter which one we call length, width, and height, because we know that multiplication is commutative. We can multiply in whatever order we want. So why don't we just put the x first? So we got x times 10 minus 2x times 12 minus 2x. Okay, there you go. Write a polynomial function describing the volume of the box as a function of x. Done. Hooray. Okay, we're not asking anything else really about that. Well, I guess what's the applied domain? So I think we talked about this in a previous section where we've got a math object, we've got a polynomial, right? But this is only going to make sense for certain values of this variable. I think the example that we looked at before was like if I had a basketball, I'm going to shoot a basketball and I'm going to fire it at this net over here, right? I'm going to try to hit that net. So I would throw my ball, goes up and then it comes down, and then it would kind of change direction, right? So here this would look sort of like a parabola, but everywhere else it's not going to behave like the parabola, right? If I would take and continue this on, my parabola would keep going that way, and my parabola would keep going this way, right? But it doesn't really make sense to use that math model to talk about the path of that basketball, because we can see it, it's going to hit the backboard or it's going to hit the floor, and it's not going to go backwards. So it really only makes sense in this context here between 0 and whatever that is. I don't know what value that is, doesn't really matter. The point is, there are some values of this variable that aren't going to make sense to use this math model. So think about what it is that we're actually doing. We're taking a piece of cardboard, it's 10 by 12, and we're going to cut the square out. So if I cut a square out here and a square out here, we want to think about the boundaries of the distance we can cut. Now, if we don't cut anything off of here, we're going to be left with a sheet of cardboard, and it's not going to be a box at all. So right away we can say that the value 0 doesn't make sense to put in there because, hey, we're not going to have a box, right? So we could say our domain, we can kind of start with it. We know it can't be 0. And would it make sense to put a negative number in there? What would that even correspond to? If I'm putting a positive number, this is what I'm going to cut, right? So if I were putting a negative number on there, I would want to cut a negative length. And what would that even mean? I think that would probably correspond to adding to our piece of cardboard, but that doesn't make any physical sense. It's not like we're going to, tape an additional piece of cardboard on there. So anything less than 0 isn't going to work either. So we know 0 is not going to work. Nothing less than 0 is going to work. Well, what's the top end? Well, think about what we're doing again. We're cutting a chunk out of each corner. Well, if this dimension here is only 10 units, how much can we cut? Like if I tried to cut 6 inches off of this side, well, I don't have 6 inches I can cut off of that side too, right? These squares have to be congruent. They have to be the same. So the maximum we would be able to cut here is 5, right? So 5. In the other direction, we can think about it in the other direction too, right? But the maximum we'd be able to cut there is 6. But we want to think about the lower of the upper boundaries here. So if I cut off 5 inches, what's going to happen? Well, I'm cutting everything, right? So then we're not going to even have a box. We're just going to have a little sliver of cardboard here, right? So that's not going to be a box. So we would not want to include 5. So hopefully that made sense. we got to think about the physical context that we're trying to model here. So be careful with these. All right, consider the graphs of power functions. Okay, power functions. So these look like this. Oh, that's pretty ugly. Okay, so power functions look like this. So let's make our lives just as easy as possible. Let's consider where a is bigger than 0. So let's say a is 1. And it doesn't exist. I mean, we could choose 2 or 3 or 4 or 5, whatever we want, but it's going to be the easiest if we just say, hey, let's let a be 1. And on this other side, let's consider where a is less than 0. And maybe we could say just a is -1, right? So let's just draw, I don't know, a bunch of them. So let's say n is 1. Well, that's going to be f of x equal, if a is 1 and n is 1, that's just going to be x. And we just immediately know what that looks like, right? It's that identity function. Pretend it goes through the origin. Cool. Now if I have n equal 2, and we're going to use the same coefficient, right? 1, I've got x squared. We're intimately familiar with what this looks like, right? We can draw the picture there. Okay, n equals 3. We can do the same thing. So we know 1, 1, 0, 0, -1, -1's on there. We know that the pattern looks like this from our previous work. And we can keep going, right? So f of x equal x third, f of x equal x to the 4. And we can kind of guess in our heads what we think this is going to look like. If we need to go plot points, you should go plot points. But we can at least take the 3 buddies we've got, -1, 0, and 1, and put those in there, right? -1, if I raise that to the 4th power, that's going to be 1. Put a 0 in there, we got 0, right? 0 to the 4th is 0. 1 to the 4th, well, that's 1. So the pattern that we see is kind of looking like this, and it should look kind of like this. But the difference is, what's going to happen if you put a 2 in there? If you put a 2 in there, you're going to get 2 to the 4th power, and that's 16, right? If you put a 2 in this one, you're going to get 4. So this guy here, outside of the interval -1 to 1, is going to get much larger, much faster. So it's going to be looking more kind of like a vertical line there. And then inside there, when we raise a fraction to the 4th power, multiply the fraction by itself over and over, our values inside here are going to be closer to 0. So what that means is it's just going to look more boxy inside the interval -1 to 1, and it's going to look more vertical outside that interval. All right, we can do the same thing with n equal 5, right? N equal 5, f of x equal x to the 5, and we can draw a picture of what that looks like, right? And we would do the same thing, right? Put a 1 in there, 1 to the 5th, that's 1. -1 to the 5th, well, that's -1. And we can, sketch the graph. We got the nice pattern. And the same thing's going to happen as happened with this one here. The higher the power is, the faster it's going to go. Up or down, I guess. It's going to look more vertical outside the interval -1 to 1. And it's going to look more, because I could probably draw a better picture of what this should look like, because it should look more boxy sort of inside those regions. But what we want to latch onto here is the pattern that's happening. So when we have a coefficient that's positive in front of these, 1, we can lump these all in with all the positive numbers, right? So consider maybe putting a 2 there. What's going to change? Thinking about this in terms of transformations, if we have a 2 in front, like if I had a 2 in this position, it's just going to stretch it vertically, right? But it's going to essentially have the same pattern. It's going to go up on one side, go down on the other, or it's going to go up on both sides. So, right, and we can see where the pattern is happening. We've got n equal 1 goes up on the right, down on the left. N equal 3 goes up on the right, down on the left. N equal 5 goes up on the right, down on the left. And we can see the pattern with all of these even numbers too, right? 4 and 2, they both go up, right? So all go up on the right. The odd ones go down well, I think we're going to generalize this more later, but what we should notice is that they all go up on the right and the odd ones go down on the left. So I'm not sure if we even really have to do very much for if our function has a negative coefficient. Think about what happens with transformations here. If we have transformations, maybe I can draw these. If I have a negative in front of there, that's just going to flip it about the x-axis, isn't it? If I have a negative here, it's just going to flip us about the x-axis. If we got a negative in front, we're going to flip about the x-axis. Negative in front. You know, the same sort of thing happens with all these patterns, right? We just flip it about the x-axis. So all of these positive ones, I'm getting kind of cluttered up here. All of these positive ones are going to all go up on the right-hand side. And we can say that all the negative ones, they're all going to go left, or excuse me, they're all going to go down, not left, they're going to go down on the right-hand side. Okay, so good. Here we're going to generalize this. So n behavior of functions where n is even. So goes up on the right. Same on left. For a less than 0, this goes down on the right. Same on left. So graphs look like, you know, they're going to look like this, or they're going to look like this on the ends, right? This is n even a bigger than 0. This is n even a less than 0. So great. When n is odd, well, it's going to do what we said it would do earlier, right? So for a bigger than 0, we're going to go up on the right, opposite on the left. For a less than 0, it's going to go down on the right, opposite on the left. So our graphs are going to look like this, right? Up on the left, down on the right. Or excuse me, I said that backwards. Up on the right, down on the left. This is where a is bigger than 0 and is odd. And if a is less than 0 and is odd, then it's going to do the opposite. So it's going to go down on the right, up on the left. Okay, good. So end behavior is a pretty big deal, and it's one of the things that we're going to be looking for polynomials. And we're going to point to power functions later to decide are we going up or are we going down. Okay, so next, intermediate value theorem. So the intermediate value theorem, this is a fairly intuitive concept, but the mathy version of this is kind of ugly looking. So let's draw a picture and we can make some sense of this. So suppose that f is a continuous function. We remember what continuous means, right? We can draw it all with one pen stroke or one pencil stroke. We can draw the whole thing without picking up our pencil. So if I have some function that is continuous on an interval, let's say it contains a and b. Let's put a here and b here. And it's continuous, and the interval contains both a and b. If f of a and f of b have different signs, so that means one has to be positive, one has to be negative. So let's say that this one's positive, this one's negative, right? So these values have different signs. This would be the point a comma f of a, and this is the point b comma f of b, right? So down here, this is f of b, and up here, this is f of a. Okay, so if these things have different signs and it's smooth and continuous, let's just stop right there. If it's smooth and continuous, that means that there has to be a line or a curve connecting these 2 points. And we don't know what it looks like. You know, maybe it looks like this, or maybe it looks like this, or maybe it looks, you know, I don't know, like this. We could look like this. But no matter what, if I'm going to draw a line that connects those 2 points, it's got to touch the x-axis, right? And that's the whole thing with this intermediate value theorem. There has to be a number, at least one, right? At least one value where it touches the x-axis here. So f of c would be 0. And that's what we're saying here. So if I've got a point, right, if I've got a point above the x-axis and a point below the x-axis, as long as this thing's smooth and continuous, there's got to be at least one value that makes it, well, between those two. This is a really powerful theorem. We use it a lot. You may see it in calculus if you go take calculus. But we're gonna use it here to find zeros, right? Finding zeros using this is kind of misguided because we're not exactly going to know, how to restrict this. What we will use this for, though, is kind of, I guess, hidden in what happens here. So let's talk about the steps that we're going to do to construct a sign diagram, and then we can talk back about how that intermediate value theorem is going to help us. Okay, so steps for constructing a sign diagram for a polynomial function. We did this with quadratic inequalities. You remember this when we were solving quadratic inequalities? We found all the zeros of the quadratic function, and then we put those on a number line with 0 above them, and then we picked numbers between each of these to say, well, hey, where is the function in this interval? So let's do this. So find the zeros of f. So we want to find all of these zeros, right? Well, we know that if I've got a string of things being multiplied together, if I have two things being multiplied together and their product is 0, then that's going to tell us that either A is 0 or B is 0, right? And that's for any number of factors. We could put ABC equals 0, then we could say, or C is 0, blah, blah, blah. So this 0 product property is a pretty big deal. And that's how we find zeros, right? We're going to solve f of x equals 0, and that's exactly where this plays in, right? So either x squared is 0, or x plus 3 squared is 0, or one of those factors has to be 0, right? So we've got or x plus 1 equals 0, or x squared plus 2 equals 0. Okay, well, if any of these things are, well, 0, that's what we want. So we can solve these, right? This one we would have x equals 0, that's it. This one we'd have x equal -3. This one we'd have x equal 1. And this one we'd have x equal, what is this one going to be? Plus or minus square root of -2. So this has no real solutions. All right. So our only zeros are this one, this one, this one. Yeah? Okay. So let's construct this sign diagram. So we found the zeros, put them on a number line with a 0 above them. I'm going to get that out of the way. Here. Okay. So let's put those on a number line. We've got -3 is here, 0 is here, 1 is here. And we got a 0, 0, and a 0. So what we're constructing here is our number line. So here's our x values, and these are our f of x values. And above the line, we're going to have function values. Below the line, we're going to have x values. Okay, so we want to choose a real number in each of these intervals. So we've just split ourselves up into 1, 2, 3, 4 distinct intervals. And we want a test point in each one of those. So maybe -4 would work. Just pick an easy number here, right? -1, maybe a half, probably pick 2. And what we're going to do with these is we're just going to determine the sign. All we care about is the sign, and that's it, right? That's the only thing we care about here. So going up to the original function, if we put a -4 in there, what's going to happen? Well, if I square a -4, that's going to be positive. If I have -4 plus 3 and square it, well, that's going to be positive. If I put a -4 in here, I'd have -5. That's going to be negative. -4 squared, that's positive, plus this one's positive, right? So I've got a positive times a positive times a negative times a positive. That is going to be a negative. Okay, we can do the same thing for -1, right? Square -1, it's always positive. -1 plus 3 squared, well, that's 2 squared, that's positive. -1 minus 1 would be -2, that's negative. And then this guy, -1 square plus 2, that's positive, right? So our net result here, positive, positive, negative, positive, that's going to be negative. All right, so now that we've done 2 of those, maybe we can notice something else that's going to kind of lead us into what we're going to talk about next. If I square any number at all, or for that matter, if I raise any number to an even power, isn't that number always going to be positive? So this number here, no matter what, that's always a positive number. That one too, no matter what, it's always a positive number. This one here, always positive, right? Because the squares are always positive, then add 2, hey, it's still positive. So really, the only piece that matters when we're finding the sign of this is that one, right? That's the only one that could be either positive or negative depending on our x value. All the rest of these are always positive no matter what x is. I guess this one is 0 if we put x equals 0 in there. So maybe more properly we can say that they're always non-negative, not necessarily always positive, but always non-negative. Anyway, if I put a 1/2 in there, that's going to be positive, that's going to be positive, this is going to be negative, and then this one's going to be positive. So net result would be a negative in that region. And then we can go do our other test point, and the only one that really matters, which again is this one, 2 minus 1, well, that's 1, so it's positive, so we're going to be positive here. So what we've done it. We've found a sign diagram for this, and this is going to be what helps us draw our picture. So I don't want to get too far ahead here, but we can already start thinking about what the picture looks like, and we should. We know that -3 is a 0, we know that 0 is a 0, we know that 1 is a 0, right? And what we've just shown with our sign diagram is that all the values to the left of x equal -3, everything is negative there. So that means that it's going to go down, right? It's never going to come back up and go up because, well, I don't have any other x-intercepts. And also, we've said that it's always negative, right? So we know that's going to not come back up after it goes down. In this region right here, between -3 and 0, we know that all those function values are negative, so we know that the graph has to look like this, right? If it's smooth and continuous, it's going to have to connect those dots in some way, and what we've shown with our test point is that any point between those two x values has to be negative, below the x-axis, right? That would correspond to a function value being negative. Same thing's going to be true about that region, but once we get to the right of once we get to the right of x equal 1, then it's going to go up. So really, really rough sketch of our graph. There we go. And it all really relies on what are the zeros and what are the signs of the function between those zeros. So something we might further say or further inspect is why didn't we change sign? And that has to do with what we were talking about with the square, right? If I've got an even power on any of these zeros, that's always positive, or always non-negative. So that's not going to have any effect on what the sign of the whole polynomial is. But I don't want to get too far afield there. So let's go on here. End behavior. So yeah, this said what's happening in the middle of the function, and then we're going to talk about what happens on the ends of the function. So we got another mathy kind of statement here. Let's look at an actual one. So f of x equals, 3x to the 4 minus 5x to the 3rd plus 7x to the 5th. Okay, so if we had to just guess which one of these terms has the most influence over what happens on the ends, which piece would we guess? Well, what might help us with our guess is to think about what happens on the ends. So as x goes toward infinity, right? Or as x goes toward negative infinity. So we're thinking on our graph, as we go this way or we go this way, what's going to happen? So if we put in something really, really big, say maybe x equal 100, think about what's going to happen here. We're going to have, we're going to have that this piece is going to be 3 times 100 to the 4th. This piece is negative 5 times 100 to the 3rd, so that's going to be smaller in magnitude than this. And then this piece is going to be the biggest of them all, right? That's going to be 7 times 100 to the 5th, and that's going to be really, really big, right? So the piece with the highest degree is going to have the most influence over our function as our x values get larger and larger and larger. Well, that's exactly what we're saying. That's exactly what we're saying right here. So the end behavior of any polynomial function at all, on the ends, it's going to do what the leading term does. So the ends look like the power function corresponding to the leading term. And that is a big deal, right? Because we just talked about what power functions are going to do, right? So, and go back up and see the end behavior for power functions. Okay. So end behavior for power functions. We'll get back to end behavior in a second, but we've got another definition for multiplicity. So suppose f is a polynomial function and m is a natural number. Here we go. If x minus c to the m is a factor of the function, but x minus c m plus 1 is not, then we say that x equals c is a 0 of multiplicity m. So here's an example, because I know that that's kind of mathy looking. So here's our function, which is also going to be mathy looking, by the way. Okay. That's fine. Okay, so we can say what the zeros are, right? 1, x equal negative 2, x equals 0. Multiplicities are, so bottom line here, we're just looking for the number up there, the highest of these numbers, and that's going to be called the multiplicity. So the multiplicity of this 0, the corresponding power here is a 3. This 0 here, the corresponding power is 5. And this 0 here, right here, corresponding power is 4. And if you're saying, hey, is it that easy? Yeah, it's that easy. So we just look to see the highest power that is attached to that 0, right? And we say that this one has multiplicity 3 because x minus 1 to the 4th power is not a factor, right? And that's just fitting it exactly into the nice definition. So we're just looking at the exponent that's attached to each of these zeros. Okay, so the role of multiplicity, what's going to make this convenient for us is that we're going to be able to tell what happens at a 0 or around a 0 on a function. Well, think about the easiest things we can, right? So if I have y equal x squared, our 0 here is, well, 0. And what happens on this graph? Well, the power, if I've got an even power, that object is always, always, always positive or 0. It never changes sign. It's either 0 or positive, right? So graphically, that means it's always above the x-axis or on the x-axis. It's never below the x-axis. So if m is even here, if our multiplicity is even, our function does not change sign, which means that it's only going to touch the axis. It only touches the axis, right? Now think about our typical example with an odd power. Well, that's our cube function. And this object does change sign as we move through that 0, right? If I take something left, like if we're arranging this on a number line, if I take something left and I cube it, it's always going to be negative. If I take something to the right and I cube it, it's always going to be positive, right? So it switches signs here. So this is going to crosses the x-axis at that 0. Okay, so I think we're now equipped to draw some serious graphs here. So sketch the graph of this function here using end behavior and multiplicities of zeros. All right, end behavior. We want the leading term, right? We can multiply this whole thing out. If we really, really wanted to multiply this thing out, we can. But we don't want to do the work if we don't have to do that. All we care about is the leading term. So if we think about what we're going to get if we just multiply the leading stuff together, well, what are we going to get? If we want to, we can write it out again as -3 times 2x minus 1 times x plus 1 times x plus 1, right? And then it might be more clear that if I want the leading term, I'm just going to multiply all of these things together, right? So I would have x times x is x squared times 2x would be 2x cubed times -3 would be -6x cubed, right? So we're just taking the largest power in each factor and multiplying it together. And there we go, we've got it. So if our leading term is -6x to the third, we're going to say what the end behavior is, right? So in this case here, our coefficient is less than 0. This means it goes down on the right. And we have n is odd, so it does the opposite on the left. So right away we can start drawing our picture, right? We know it goes down on the right, so down on the right. We know that it goes opposite on the left, so it goes up on the left. All right, we're on our way. Okay, now we want to know what happens at the zeros, right? So zeros are, what are they? X equal what? This one would give us 1/2. This one would give us -1. And those are the only two zeros. Okay, how about the multiplicities? Multiplicity of this guy would be 1, and that's odd. Multiplicity of this guy going back up to the original one, the power there is 2. It's even. So that means that we're going to cross here, and we're going to touch here, but not cross. So we've got x equal 1/2 right there, x equal -1 right there. We know that we're going to touch the x-axis at x equal 1. So it has to, connect the dots, right? So we're just going to touch there. If we want to make an even better picture, put your y-intercept on there too. Every time we find y-intercepts, we're just going to crank a 0 through the function. So if we do that, we'd get -3 times -1 times 1. So that's going to be +3. Okay, so we knew that it had to go up on the left. Darn it. We knew that it had to go up on the left. That was from our leading term. So, hey, look, it's going up on the left. And we know that we've got to come and touch this point here because we know it's an x-intercept. We know that it bounces right back because it's got even multiplicity. It has to go through that point right there because it's a y-intercept. Now from our y-intercept, we know that it's got to come down and touch that point, and then it's got to go down on the right. So down on the right. And that's all. I mean, we can draw a more beautiful picture if we use more test points. Put more test points on there. Put something -1/2 in there, maybe. Put 2 in there and make a better picture. But really, the essential thing is, what are the zeros? What's the end behavior? What are the multiplicities of the zeros? And we can draw a really, really rough sketch of the graph. Let me write another one here, and we can look at another. All right. So here's another example of a polynomial. We want to draw the graph. I guess I didn't write that in there. Sketch the graph. Sketch the graph using end behavior and multiplicity of zeros. Okay, so end behavior. Again, this is going to be our leading term. Now to find our leading term, we just want to multiply all of the highest degree multiply out all of the highest degree items here. So the largest degree on x from this term is going to be a 1. Highest term on this is going to be x cubed, right? If we multiplied all these things out, x cubed is going to be the highest power on x. This one here, the highest power on x is going to be x squared. and this guy here we're going to have 2, right? So if I multiplied all those together, the highest powers, well, it's 2 times x squared times x to the 3rd times x, so that'd be 2x to the 6th. Okay, so now we have that a, our coefficient here, is bigger than 0. This means it goes up on the right. And n is even, so that it does the same on the left. So if we're going to start our graph, we know that it goes up on both the right and the left. And now we're going to use the zeros. So the zeros are, I'll just go on down the line. We've got x equal 3, x equal -1, x equal 4. So we can say what their multiplicities are. Multiplicity of this guy, well, that power is a 2, and this is even. And multiplicity on -1, so that'd be a 3, that's odd. Multiplicity on x minus 4, so that multiplicity is 1, and this is odd. We're saying even versus odd because that's what we're going to do to say, you know, this is the behavior. Even, it's just going to touch. Odd, it's going to cross. Odd, it's going to cross. Okay, so we can draw a rough sketch now. So I've got -1 is a 0. I've got 1, 2, 3 is a 0. 4 is a 0 as well. And it's just now a game of playing connect the dots, right? So on the left-hand side, I know it's going up on the left, and that's great. At some point, it's got to go down and touch that. Well, this one has an odd multiplicity, so that means we're going to cross the x-axis. So it's going to go down below. And then again, we can find our y-intercept, f of 0, right? So this is going to be 2 times -3 squared times 1 cubed times -4. So what is this? 2 times 9 would be 18 times 4 is, you know, some number down here, and we can find that, right? We can compute that. That's not exactly the point. The point is that there is an ordered pair down there that the function also goes through. Okay, so that's wonderful. And then after we get out of this point, moving to the right, well, we know we have to go and touch that. Well, what's going to happen at x equals 3? Well, the multiplicity of that 0 was even, so it's just going to touch and bounce right back. And now it somehow, some way, it's got to go back and touch the axis at x equals 4. We know that's odd multiplicity, crosses, goes right through it. And hey, there's a really rough sketch of our graph, y equal f of x. And really all we used is multiplicities and endpoints. This point right here, we can compute that, right? We know how to do 18 times 4. We do that by hand, or take 8 away from 80, 72, right? So that'd be a pretty large number down there, but that's not exactly the point. The point was what's happening around our zeros, what's happening on the ends of a polynomial. So something that we should notice is that this function right here that we were given, it's already factored for us. So the hard part is done, right? The factoring is going to be the hard part, and that's where we're headed, because we're just going to be given a polynomial in standard form, right? So we're going to be given something that might look like, x to the 5 plus 3x to the 4 minus 2x plus 1, and we're going to say sketch the graph. We're going to do the same things and find the zeros, but we're going to have to factor first. At this point we would say, well, do I have a general factoring rule for a 5th power polynomial? And we don't right now. But anyway, that's where we're headed. But we can do an awful lot with what we already know about polynomials. So with behavior and multiplicities of zeros in particular. Okay, so great. That was it. Thanks for watching the nice video, and have a great rest of your day.